Hello everyone, welcome back to Eurohub and welcome to the series of lectures in gate concept. And we were discussing flight mechanics. In the previous lecture we discussed about thrust required for level and accelerated flight, and also we discussed about minimum drag condition. In this lecture we will continue the discussion about minimum drag condition, as well as we will discuss about drag polar. Okay, so we have the famous equation CD, which is equal to CD naught plus CDI. CD naught is nothing but the zero lift drag. CDI is nothing but the induced drag. And from the previous lecture, I can write CD naught is equal to CD is equal to CD naught plus CDI is equal to K CL square, and the value of K is equal to 1 by pi into E into AR, where E is the efficiency factor, AR is the aspect ratio of the wing. Okay, and for a steady level flight, lift is equal to weight, and you can write lift is equal to weight as half rho v square, that is nothing but the dynamic pressure, into the wing area S and the coefficient of lift CL. From equation number 2, I will find out the value of CL. Okay, so I will be getting this expression, that is CL is equal to 2 times the weight of the aircraft upon rho v square S. Okay, CL is equal to 2 times the weight of the aircraft divided by rho v square S. Rho is the density, v is the velocity, S is the wing area. Okay, now I'll substitute equation number 3 in equation number 1. I'll be getting CD, which is nothing but the drag coefficient, is equal to CD naught plus K into, instead of CL, I'll substitute as equation number 3, 2W divided by rho v square S the whole square. This is equation number 4. Now what I will do is I'll multiply equation number 4 by this term half rho v square S. Okay, so I'll multiply equation number 4 by half rho v square S in both side. Okay, in both side, in the both side of the equation number 4, I'll multiply by half rho v square S. So I'll be getting this equation, half rho v square S CD is equal to half rho v square S CD naught plus half rho v square S K into 2W by rho v square S the whole square. Okay, so in this is nothing but for zero lift drag, and this expression is for the lift induced drag. Okay, I can cancel this part, half rho v square S, because we have a square term, and I can cancel out this 2, and 2 square will be 4. Finally I will be getting 2. Okay, so this equation become capital D. Okay, half rho v square S CD is nothing but the total drag. Okay, drag is equal to, total drag is equal to a v square plus b by v square. Okay, a v square plus b by v square. If you observe this equation, I can write d is equal to half rho v square SCD. Okay, a is nothing but half rho SCD naught. Okay, this is a half rho SCD naught. Similarly, this part, this b is nothing but 2 into k, we have a term left k, 2 into k w square divided by half divided by rho S, not half, rho S. Okay, so D is equal to, the total drag is equal to A into V square plus B divided by V square. And you can see here the profile drag is proportional to V square. Okay, from this equation I can get an idea. The profile drag is proportional to the velocity square, and the induced drag is inversely proportional to the velocity square. That means the profile drag will be increasing with respect to the when velocity is increasing, and the induced drag will be decreasing when the velocity is increasing. You can see the plot between the total drag and the airspeed. Okay, y-axis we have the drag, and in x-axis we have the airspeed. And you can see here, in the case of profile drag, the profile drag, we have the drag is proportional to v square. When the velocity is increasing, the drag is increasing. This is the plot for profile drag. Okay, and for induced drag, when the velocity is increasing, the drag is decreasing. Okay, you can see here, the velocity is increasing, the drag is decreasing. Okay, and At the intersection of these two curves, we have the minimum drag. Okay, and this curve corresponds the total drag of the aircraft at a particular altitude. Okay, this is for a particular altitude, not for every altitude. This is for a particular altitude of a given aircraft. Okay, and if you connect the intersection, if you take the line of intersection of both the profile, I'll be getting something called the total drag of the aircraft. Okay, minimum drag for the aircraft. This is the minimum drag for the aircraft at a given altitude. Okay, so this is all about drag polar. This is basically a symbol you have to always understand. When you have increasing velocity, there will be decreasing induced drag and there will be increasing profile drag. Now we will discuss about minimum drag condition, and also will derive some important relations that is useful for the gate examination point of view. In the last lecture, I have discussed that the CL for a minimum drag is root of CD naught by K, and also the CD for a minimum drag is 2 CD naught. Okay, these two are really important relation. You have to remember these two relation. Okay, then we have certain important relation. TR, that is thrust required upon W, the wall square is equal to. Okay, so we have the equation thrust required is equal to W divided by CL upon CD. So I can write TR by W will be equal to CD by CL. Okay, just squaring this term. So we have the value for CD. CD at minimum drag is 2 CD naught, and the CL for minimum drag is root of CD naught by K. Okay, we have CD and CL. We are just squaring. I'll be getting 4 CD naught square, and we have CD naught by K in the denominator. Okay, I can cancel out one CD naught and K will be going in the numerator. So finally I'll be getting 4 CD naught K. This is really an important relation. And L by D max is equal to CL of minimum drag by CD of minimum drag. And we have CL of minimum drag as CD naught by K and CD of minimum drag as 2 CD naught. Okay. And if I am solving, I'll be getting, I can cancel out one, this root of CD naught will, so there will be root CD naught at the denominator, and I'll be getting 1 by 2 into root of CD naught K. So I can write finally as L by D max is equal to 1 by root of 4 CD naught K. Okay, these two are one of the important relation in minimum drag condition. In the next lecture, we will derive the expression for minimum drag. Okay, that's an important concept for gate examination point of view. Thank you for listening this lecture. Take care.